He was born in 85.
Shall I start recording?
It is.
So today we get to talk about computational fluid dynamics and finite element analysis. Now, I have to begin today's lesson with a very important disclaimer, okay? And that is, we are not teaching you everything you need to know in the next 50 minutes to go out and do this professionally. In fact, we're not even scratching the surface of what you need to know to go out and use these kinds of tools professionally. There's some professors in the MAE department that do not want us to show you this at all in here because they feel like we're giving you a tool that you don't really know how to use, and that just can be dangerous. And they have a valid point with that. But we do go ahead and show it to you anyway. Okay? And this is only the second semester we've included this material in this course. So you're among some of the first students to see this as part of this course. The reason we go ahead and show it to you is a couple reasons. First of all, we want to show you that there's some very advanced capabilities that are possible in SOLIDWORKS with the models that you've been working hard to make all semester long. The other thing is, we hope that at least some of you will be interested and excited by this, and if so, you can pursue further study of these topics in your academic career. There's an entire course in MAE devoted to computational fluid dynamics, and that's MAE 6263. There's an entire course devoted to finite element analysis, MAE 5563. So if you take these courses, they will show you and teach you some of the theory behind what the computer is doing, and that will enable you to use these tools more knowledgeably. But the bottom line is, these tools, or their results, are only as good as the person using them. And so if you try to run one of these analyses, but you don't really know what you're doing, you don't fully understand it, what can easily happen is you make some mistake, and you get results that look perfectly fine. But in fact, they are completely, flat out wrong. And if you under-design a car or an airplane or a bridge based on an erroneous CFD analysis or FEA analysis, people could get killed. There's very serious consequences that can happen from getting bad analysis results. So, that being said, just realize, well, I guess the other reason is, even if this doesn't interest you and you don't choose to go on and study it further, at least you've seen it. And if some other engineer comes up and talks to you about an FEA or CFD analysis they've run, at least you have some clue what they're talking about. Okay? So, that being said, we'll go ahead and get started. Your question?
Is it possible to take those courses as an undergraduate?
As far as I know, it might be possible when you get up to choosing some of your senior electives. I don't know for sure, but it certainly seems possible. Okay, so both of these are, let me get this turned off. Both of these tools are add-ins that don't come in the basic SOLIDWORKS package. So, do you remember in SOLIDWORKS, how do we turn on those extra add-ins? Where do we go? Tools. Add-ins. Very good. Tools, and then all the way down to add-ins. Okay, the one we're using today, SOLIDWORKS Simulation, is the one for FEA, and SOLIDWORKS Flow Simulation is the one for CFD. So we want to turn on both of those add-ins.
What were the name of those again?
SOLIDWORKS Simulation is the first one, and then SOLIDWORKS Flow Simulation is the second. So I'll activate those and give SOLIDWORKS a moment to get them loaded. And what we're going to be illustrating these tools with is just a very simple, like a road sign. Okay? So we're going to apply a wind load to this sign and see what forces are generated, and then we're going to run an FEA study to see what kind of stresses and deflections result from those aerodynamic forces. So this simple model is something that you can download from D2L just so you have all the same dimensions that I used here. So when we turn on the add-ins, we now get a flow simulation tab and a simulation tab up top. So we're going to start with the flow simulation tab. And what we'll do is just walk through this wizard to set up the CFD study. So I'll click the wizard button. And there's several windows here we're going to step through. So first we can give it a project name. I'll just call it sign. If you have different configurations in your model, like we've talked about in the past, you can choose which one you want to run an analysis on. We'll click next. Now this is where you can choose your unit system. I'll go ahead and just accept SI units. And it shows you down here at the bottom exactly what units are going to be used for each quantity that's involved. We'll say next. Okay, so now we choose the analysis type. And SolidWorks can do internal flows. That would be like pipe flows, or like if you wanted to analyze the heat transfer within your computer CPU case, that would be an internal flow. But for this example, we're going to be doing external flow. You have options here if you want to exclude internal cavities, like if you're analyzing a tennis ball that you hit through the air and you don't want to worry about the air that's inside the tennis ball, because that has no bearing on the motion that you're going to get. You can choose to exclude those, and that will just exclude those cavities, and that will just make your analysis run faster. Now, there's several options that you that you can choose to turn on out here. If you want to analyze heat conduction or heat radiation, you can select those. If you want a time-dependent solution, you can turn that on here, a time-marching solution. And that really is what we have in this scenario, right? I mean, if you stand behind a road sign, it's not going to be just some steady state breeze blowing past you, right? You're going to be buffeted all over by the changing wind velocities and the aeroelasticity of the sign. But this also takes a lot longer. So I'm not going to do a time-dependent solution here. We're just going to do an average, kind of an average steady state kind of a solution. But that means we're presenting error into our solution by not representing the physics accurately. If you wanted to turn on gravity, that would be very important for like if you're doing if you've got buoyancy effects or thermals. And then finally, rotation. You can analyze the airflow past like a rotating propeller or a turbine or some object like that. For our purposes, we're going to leave all of these blank and just choose the external flow. Go ahead and click next. And this is where we choose the fluid that we're operating in. So we'll just choose air, so expand gases and double click air, and it gets added down here. But as you see, you can do liquids, a variety of different types of fluids that are built in. And down here at the bottom, we choose the flow characteristic. This is where we're going to choose whether we're doing laminar flow, turbulent flow, or both. Now, in the real situation, if wind was blowing this way and encountering the desk, it would probably be laminar for a certain distance, and then eventually it would trip and become turbulent flow across the desk. In this case, so you could choose to analyze laminar and turbulent flow, so that would, the computer would spend a lot of time trying to figure out where does that transition actually happen. Okay? Now, for simplicity and speed, today I'm going to go ahead and just choose turbulent, because I know the flow behind that sign is going to be turbulent, and I'm not going to worry about the laminar aspect of it at all. So we'll do turbulent only. If you had a high Mach number situation, or you needed to include the effects of humidity, you can turn those on as well. Okay, so turbulent only, air, okay, we'll say next. And this is where we can set the wall conditions such as roughness. I'm not going to make any changes on this tab. I'm just going to let it be adiabatic, which means we're ignoring heat transfer and essentially zero roughness. Click next. Okay, and this is where we define the environmental conditions. So we've got standard temperature and pressure here, 293 Kelvin and 101 kPa for pressure, standard atmospheric pressure. Now, for our analysis, here's the sign, and if we want wind to be blowing at it in this direction, we need to specify a velocity in which direction? X, Y, or Z?
Z.
In Z, and we want it to go in the negative Z direction, so that it's blowing at the sign. So right down here in the velocity parameters, we'll just go to the Z direction and change that value to -22 in the Z direction. and click next. Okay, now this screen is talking about the mesh or the grid size. If a professional CFD analyst looked at this screen, they would probably get sick and puke on you. Because this grossly oversimplifies what's going on here and what this is all about. This is perhaps the greatest pitfall in all of CFD, is getting your mesh correct. And to have it represented as just a slider from 1 to 8, from coarse to fine, it really is kind of disturbing. But there are, after we do a run with a default mesh, there is a way you can go back and have more control to refine the mesh. And I'll show you how to do that after this initial run. But we need to stop here and talk about what this mesh size is all about. So, what SOLIDWORKS is going to do to analyze this situation is going to take some volume of air surrounding the sign, and it's going to discretize it into a grid or a mesh. And so, for example, if we were going to do a CFD analysis on this room, we might take the entire volume of this room and break it up into 1 cubic meter blocks and just fill the room with all these chunks of 1 meter square or 1 cubic meter blocks of air. Now, that would give us a result. Would it be accurate? Well, we don't really know. But we could instead fill the room with blocks that are 1 centimeter cubed. Okay, much tinier. Would that give us an accurate result? Well, we still don't know, but it's going to make a big difference, right? And certainly, if nothing else, it's going to make a huge exponential difference in the runtime that it takes to run the analysis. So, and with mesh and grid size, this is kind of where the black art of CFD comes into play. This is where experience really matters in order to get this right. And there's no single answer that works in all situations. But suppose we're going to plot some results. And so this is going to be our answer on the y-axis. And it could be pressure, it could be velocity, or whatever other parameter we're interested in. And at the left side of the x-axis, we'll call that a big mesh. And at the right side, that's a small mesh. Okay? So a big mesh simply means big grid size, a small mesh. By comparison, might look something like that. So if we run our analysis over and over with different mesh sizes, ranging from big to small, what we would find in our answer is it would change depending on the mesh size. So the first time we run it with a coarse mesh, we might get an answer up here. And then we run it with a smaller mesh, maybe we get an answer down here. And then a smaller mesh, we get an answer here, here. Okay, so connecting these dots, we're getting something that looks kind of like that. So each one of these is a different answer that our CFD study gave us, depending on which mesh size we use. Which one of these is correct?
All of them?
In a way, all of them are. Okay? Certainly, SOLIDWORKS is not going to tell you any of these are wrong. SOLIDWORKS will present them as correct answers, but they're certainly different. And if we assume that there is one correct answer, one true state of fluid flow in this room, which one of these would you pick as the correct answer?
The smallest mesh.
Okay, this one up here? Okay, that would be a good answer. Any other thoughts?
The average.
Okay, the average, looking at all of them? Okay. Well, now let me ask, picking the smallest mesh, if we go with this one and compare it to this one, there's not a whole lot of numerical difference, right? But this one could take 100 times longer than this one to get an answer. because the mesh size is so much smaller. So which one would be the best one to choose out of those two?
All further to the left.
If you're concerned about time, maybe go with this one because it's still reasonably accurate, but it ran a lot faster. Now what's interesting, and this kind of gets into computer science issues, but if you kept making the mesh smaller and smaller and smaller out here, what would happen is, it would continue to well behave for a while, and then you would start getting all this noise again, and this is simply the round-off error in the computer. Okay, eventually your mesh gets small enough that the round-off errors start piling up, and your results go chaotic, but that has nothing to do with your mesh or has nothing to do with your analysis. It really is just the limitation of the computer. So, to run a CFD analysis and feel like you're getting good answers, you have to do what's called a grid convergence study. Okay? And that's kind of what's represented here. Because you might run your analysis with a coarse grid, and then run it again with a finer grid, and see if the answer changed. Here it did. Run it again with a finer grid, and see how much it changed. Run it again. And what you're looking for is the point at which the answer you're getting is independent of the mesh size that you're choosing. Okay? This answer up here is a bad answer because the answer is dependent on the mesh size. Okay? The mesh does not accurately represent the problem and does not give you a correct result. By the time we get out here, this is starting to look more like a correct, viable result. Okay? So, so your goal with a grid convergence study is you want to refine your mesh until the solution becomes independent of the grid size. And that's often a question that comes up on the final exam. So just keep grid convergence study, keep that concept in mind. And also keep in mind that doing a rough grid can very quickly give you a terrible answer. So this is a very important part of doing a CFD analysis. Yes?
If we really cared about the answer, would it be possible to do like a trend line analysis with a constant derivative and see where that approaches?
Like a trend line analysis on this kind of a curve, you mean?
Yeah, and just kind of like constant curve kind of to it, and like it'll approach zero as it looks like it does, approach a number as it looks like it does.
Right.
On this.
Right, so you could do that using a trend line analysis and do it sort of more formally, or like I was just illustrating it just by kind of looking at it and seeing when it flattens out.
Gotcha.
But what you're describing would be a more formal way of doing that, yeah. Any other questions about this concept? Okay. Okay, so back to our analysis that we're setting up. So all that being said, I'm just going to go ahead and leave this at 3 for now, because this will run a solution in a reasonable amount of time, and we can at least see some results. Okay, so that's the last screen. So at this point, we would just click Finish. And so you can see there, this box now is the computational domain that we're going to be analyzing. Now, the way it's set up now, your road sign is just kind of floating in midair, right? And that's not very accurate. So what we want to do is simulate the ground plane underneath the sign, and the way we do that is by changing one of these sides, the bottom side of the computational domain, to be a symmetry plane. The way we do this is go over here to the computational domain, right-click, and say Edit Definition. Okay. So this gives you the location and the type of boundary for each of the 6 sides of this domain. And in the y direction, we want to move this lower y boundary to 0 meters, and we want to change its type from the default to a symmetry boundary. Okay. You can see what that does is kind of give you a dotted line mirror image representation of this same domain existing underneath the sign. So the reason this works And this is a very common practice in CFD analysis. So here's, okay, so here's our road sign mounted on the ground, and what we're doing is saying, essentially, we're using this ground plane as a symmetry plane, so it's like we've got another road sign down here existing below the ground. That's how SolidWorks treats this domain. And the reason we do it this way is because if you think about what a particle of air is going to do as it comes in here, if it's near the ground, okay, it might come in and kind of scoot down near the ground and travel along, but it can never cross this ground plane. Because on the opposite side, if it's a plane of symmetry, there is another particle of air coming along this way and getting close like that. And if this air particle, the real air particle, crossed the symmetry line, then this particle would be trying to do the same thing, and at some point you have two particles trying to occupy the same region of space, and that would violate conservation of mass and cause all kinds of problems. So that's why this technique works, because it obeys conservation of mass and knows that if a particle of air is above this ground plane, it can get close to the ground, but it can't ever cross it. So that's what we've got set up here. Now, for this illustration, I'll also go ahead and drag in the boundaries a little bit closer just to save some computational time. Because this box region, this is the region that's going to be filled with the mesh or the grid of elements to solve what the fluid flow is doing over this region. Okay, so with that, we've set up enough information about the analysis, and we can go up here to the Run button and simply click Run again, and it's going to solve. So it's going through and setting up the problem. Down here, it will give you an estimate of the computation time. Even though we told it not to do a time-marching solution, we told it to do basically a steady-state solution, it is going to make multiple passes through the domain to try to refine that solution. So this is telling you that for one iteration through the domain, it's going to try to make, or it's going to do 58 iterations for one travel or one pass through the domain. And right now you can see it's at 31, 32, 33. So they're not taking immensely long to run. If you want to see what the computer is doing, there's a little preview button right up here, insert preview, and let's say cut the right plane, display pressure, you can say OK. And you can see with each iteration what the fluid flow is looking like. So you see high pressure up here, low pressure behind the sign, and it's evolving as SolidWorks tries to refine the fluid flow. But having this open does significantly slow down the computer, because every time it calculates the result, it has to show you a graphic. So let's just close that so it'll speed up and go faster.
In the meantime, did you say this was on D2L?
Yes. Do you not see it?
I don't see it.
Okay. I apologize. I think I forgot to turn it on, essentially. So I'll do that as soon as
Okay.
we get done with class. Actually,
You got
I'm going to stop this when we get up to maybe.
It's doing 1.5 travels, so it'll do more than
105, 16.
Well, it's going to make multiple passes, and it would probably go up to around 300 or 350 iterations. But once it gets through 2 travels, I'll go ahead and stop it, because I think that'll be enough for us to get some results that we can look at.
Is this simulating different sections of the sign in one travel?
So this is focused more on the space around the sign and not so much on what's happening inside the sign. So it's like the sign is there as a barrier to the fluid flow. Okay, let's go ahead. I think I can stop this. Results, yes. And okay, now I did mention that you could look at the grid or modify the grid. Let's see. I'm going to hide the computational domain just so that's not in the way. You can right click and say hide. If we go to, if I right click on the mesh, I can, let's see. Should let me show it. Well, there's a mesh button right up here, initial mesh that I can click on. Okay, so here's the box that we saw before for defining the mesh. If you turn off automatic settings down here, then you do get quite a few extra controls and parameters that you can use to refine the mesh more appropriately for